Hi, I'm Agustin Reyna, and along with Gaurav Saxena, this is a presentation for the poster from our paper on distributed PostgreSQL as an internal development platform primitive. Talked about multi-region topology and how we executed a tail latency remediation. This poster is presented in the IEEE Cloud Summit 2026 in Washington, D.C. on June 25 and 26. So this poster is about a practical platform engineering problem. What happens when PostgreSQL compatible workloads move from a single region world into a multi-region distributed database environment? The main story here is that we observed a representative query path with tail latency scales in the seconds. They got remediated into single digit to low double digit milliseconds, but the real takeaway here is that the database should be treated as a first-class internal developer platform primitive. Why this matters? A software-defined vehicle and cloud-connected platforms depend on back-end systems that are always available, regionally resilient, and responsive to users. A single region managed relational database is often operationally simple, but it may not satisfy the regional outage resilience or latency locality or data residency requirements. That pushes teams toward distributed PostgreSQL compatible systems, and those systems keep the SQL interface familiar, but they bring new operational complexity that application teams should not have to solve from scratch. The adoption trap is that PostgreSQL compatibility can make the migration feel like a database swap, but distributed execution changes the performance profile. Metadata access, query planning behavior, system table locality, and cross-region routing can all show up in tail latency. So the platform has to provide more than a database. It has to provide safe defaults for topology, for endpoints, routing, observability, and operations. This is the architecture pattern. The control plane is the internal development platform with the APIs and the policies, reconciliation controllers, integration for secrets, and defaults for observability. The data plane is a distributed database cluster across regions. Application teams should just have to declare their intent. For example, I need this database, these roles, these grants, and these endpoints. And then the platform reconciles that intent into real database objects with secret publication and standard connection metadata. The value of the declarative contract is a separation of concerns. Application teams describe what they need. The platform team encodes how it's provisioned safely and consistently. That includes least privilege, drift correction, region scoped endpoints, secret rotation, and default dashboards. And this moves the organization away from a ticket-driven database work into a repeatable, governed self-service. The topology pattern in this paper is replication factor of 5, or 5 full copies of the database, with a 2-2-1 placement across 3 regions for those 5 copies. Regions 1 and 2 are the preferred traffic regions where the application traffic is directed. Region 3 just adds quorum support in another failure domain, but it does not receive any traffic normally. This is an example of the kind of design choice that should be standardized by the platform rather than rediscovered by every service team. Replica placement alone is not enough. Routing determines whether the common case request paths stay local or may cross regions. The platform should publish regional load bounds for endpoints, not just raw node addresses. Clients should use local first routing on their normal operation and remote fallback only as an explicit policy choice aligned with their service SLO. The case study starts after a migration from a single region managed PostgreSQL to a multi-region distributed PostgreSQL compatible deployment. A representative interactive query path showed second scale upper tail latency at the SQL client. The key diagnostic direction was repeated catalog and metadata access on the critical path, with a catalog tablet leader in region 3 amplifying cross-region round trips for requests originating in the primary traffic regions. The remediation was staged. First, the baseline was roughly 5 to 7 seconds in the upper tail. The largest step change came from enabling catalog metadata caching, which shifted the tail from seconds into roughly the 100 milliseconds range. Then the index strategy adjustments reduced extra lookups, and prepared statements reduced repeated planning overhead. Together, all these incremental steps move the representative query path into the single to low double-digit millisecond range. Again, these are rounded directional changes from the incident response. This is not a controlled benchmark. There are 4 lessons that I would emphasize. First, treat the database as a platform primitive, not a bespoke dependency. Second, separate step change fixes from incremental polish, say. Under pressure, you need to find the dominant tail latency contributor first. Third, routing and endpoint hygiene needs to be the defaults because accidental cross-region hops can amplify the tail. And fourth, you be careful with claims. The portable lesson is a migration sequence and the platform approach, not the exact numbers. So the conclusion is simple. Distributed PostgreSQL compatible databases can satisfy multi-region requirements, but they move complexity into the topology, routing, the governance, and performance diagnosis. An internal development platform can absorb a lot of this complexity by making the database declarative, governed, observable, and repeatable. That is that's a practical pattern that I hope people take away from this poster.